Hello. It's safe to say that we are living in an age of AI, as this technology becomes adopted in many different fields. Specifically, machine learning systems are used in a wide variety of industries for bespoke purposes. The safety monitoring of these systems is crucial, particularly in safety-sensitive domains such as healthcare, transportation, and energy production. Various methods exist to ensure machine learning safety, one of which is SafeML. SafeML is a form of out-of-distribution detection which uses parametric distance measures to assess the proximity of a model's predictions to real test data, highlighting areas of classifier weakness that can be used to determine areas of uncertainty at or even before runtime. SafeML has seen many revisions through its lifetime, but none of these as of yet account for quantum machine learning systems. Quantum computing is a new computing paradigm that leverages quantum mechanical phenomena such as uncertainty and superprecision to perform calculations. Quantum computing holds promise in areas such as pharmaceutical development and financial modelling due to its ability to process vast amounts of data simultaneously, with immensely increased speed compared to classical systems. Leveraging the potential of quantum systems even further is a proposed implementation of quantum machine learning models, which seek to harness the advantages of quantum computing for machine learning tasks such as classification and regression. It is currently undecided the exact way of implementing such an idea, but one such method would be hybrid models, which take functionality from both quantum and classical ideas combined into one system. The caveat? Well, these hybrid models will encode data using parameterized quantum circuits, making them the format of state vectors and density matrices. This means that the classical distance metrics that SafeML currently uses will not be valid for computation on these types of problems, rendering the method obsolete in these circumstances. Fortunately, there exist quantum distance metrics which are compatible with data in such formats. In this project, a range of these metrics are explored and implemented as a provisional adaptation of the SafeML method to ensure compatibility with quantum machine learning solutions. To do this, we first explored exactly how SafeML uses its distance metrics to operate a safety monitoring method. It does this by computing the distance metrics between two sets derived from the data, predictions of a given class, and the true label. These instances are compared alongside model accuracy score in order to garner a level of confidence from the system that can indicate the need for human agent intervention. Quantum SafeML will work similarly, but amendments must be made to ensure that data is encoded in an adequate quantum format. And then the quantum distance measures will be computed on these sets. With this understood, several quantum metrics were analysed for their underlying formulas and their applicability to the specific needs of the method. The chosen ones were fidelity, which measures the similarity of two quantum states ranging from 1 to 0, with 1 representing complete overlap and 0 representing complete difference. Trace distance, inversely, measures the distinguishability between states, given by half the trace norm of the value between the two states. Burst distance, similarly, measures this distinguishability, but instead of yielding a probability for this like trace distance, measures the shapes of the given matrices and their overlap geometrically. It is given by the root of double the inverse of the root of fidelity for the matrices. Quantum relative entropy is finally chosen because of its applicability to information theory. It's a higher order metric which employs logarithms to compute the information loss from a discrepancy between quantum states. All of these metrics were converted into deployable functions. We additionally developed ways of encoding matrix conversion which is secured in adequate formatting with respect to aspects such as eigenvalues and positive semi-definiteness which cannot be guaranteed. Now, we apply these to a quantum machine learning model, but of course, to do this, we first must require a quantum computer.
I don't have the budget for a real quantum computer.
In fact, these machines are not commercially available and likely won't be anytime soon given their high cost and very particular required environmental conditions. As a result, we look to quantum simulation services in order to emulate quantum computing technology on classical machines. One such way of doing this is by using Qiskit, an open source Python library developed by IBM, which allows us to emulate quantum hardware and functionalities. We can use Qiskit's machine learning extension to build hybrid machine learning models. The specific machine learning models we will employ will be chosen due to their hybrid nature, allowing more accurate operation given our quantum simulation. We choose variational quantum classifier and quantum convolutional neural networks to this end. Qiskit Machine Learning has existing notebooks on properly instantiating these models. A VQC uses a feature map to encode data into a quantum state and uses a parameterized quantum circuit of quantum gates to derive predictions. In the original notebook, we run this VQC on the iris dataset, a common toy dataset for machine learning classification. We explore this model further in this exercise by also training the model on the wide dataset, a similar toy dataset also provided by sklearn. We also create a function capable of creating synthetic datasets of the type bunch to align with these existing toy sets. We modify the VQC into a reusable function, which can be reshaped to accommodate for any dimensionality of the past dataset. We now are able to train various types of the same basic model architecture across a range of different problems, which should show us general functionality of the quantum SafeML method. After running, our metric values show some interesting results. We compare to model accuracy and see that the metrics follow this relatively well. This means that the metrics are able to adequately pick up on model performance consistently across many different types of problem. We evaluate the method on this QCNN a bit differently. A QCNN, a quantum convolutional neural network, uses quantum convolution and pooling layers similar to a classical CNN, but with data in a quantum state. For the QCNN, we examine a digit dataset, another toy dataset which houses 10 classes of the digits 0 through 9 in grayscale pixelated images. We will train the neural network to classify these images and then apply the distance metrics as per the specified method. This time to each digit class and view how metric values vary between them. When we do this, we observe a wide range of results, which bodes well for ensuring that we are exposing a range of subtleties to this model. These results showcase the diverse range of aspects the method can capture, and this can be expanded upon by setting a threshold value which allows a human agent if exceeded, seen by this extra example of a quantum SafeML method applied to a kernel-based classifier. A kernel classifier uses kernel methods to pre-compute the quantum architecture, and we can then pass ad hoc data to it from which we can see the distribution of the classes. We can then compute the metric values against each data point, and then we can highlight areas where these values exceed a threshold, which, in proper implementation, can then lead to a notification system for human agents. Overall, quantum SafeML on hybrid models serves as a good beginning to the dialogue of quantum machine learning safety monitoring, and future work can expand on this by perhaps employing different distance metrics, applying dynamic threshold values at runtime, and extending the method to regression tasks as opposed to classifier problems exclusively.